In our last section, we looked at the multiplication rule, and now we're going to look at the addition rule. The addition rule is basically the OR case, the probability that A or B will be true. So whereas last time we were looking at more than one thing being possible at the same time, here we're looking at either event A or event B will occur, or it's possible they both could occur, but this is really one or the other. The previous section considered single events. This section considers compound events. When considering compound events, make sure to not count the same event twice. So here we have our same polygraph test results. Remember that we have the polygraph test was true, which means the test said the person lied. Negative result says the test said they did not lie. And then, of course, over here we have did they actually lie? If the test said true and they actually lied, that would be a true positive. On the other hand, if the test said that they didn't lie but they actually did, then that would be a false negative. And so you can see how the things go there. So, same table we had before. What is the probability that we have a positive test result or the subject lied? So, we have positive, and then we also have did lie, or let's see, positive test result or the subject lied. So these two are both lied, those two are both positive test results. So what we're looking for on top, all the possible cases on the bottom, we end up with 0.673. And then a little note, the total number of positive test results or subject who lied was not 108. Now you might say, well, where would 108 come from? Well, that would come from the 15 and the 42. That's 57, the number of positive test results. And 42 and 9, well, those are all the ones who actually did lie, which is 51. If you put 57 and 51 together, then you would have had 108. We did not do that because the 42 was both of these at the same time, and we did not want to count it twice. That would also have given us a probability greater than 1, because our denominator here, 98, that's the total possible. You cannot have a probability greater than 1. So, our formal addition rule, P, A, or B equals probability of A plus the probability of B, subtract the probability of A and B. This is basically the both case. In the above example, the probability of a positive test result was 57 out of 98, the A being positive test result. The probability the subject actually lied was 51 out of 98. Actually lied, 42 and 9, that gives us our 51. And the probability both were true, the PA and B, so this is one thing, but two things that are together in combination. So it's not two separate events, it's just one event, but both these parts are true. And there was our 42. So 57 and 51 minus the 42, which is 108, subtract the 42, and there's our 66 over 98, just like we had before. Nothing was counted twice. The rule can also be written this way, which is when it's like that, up U, that stands for the union. It's the probability of the union of A and B, which is equal to the probability of A and the probability of B. And then notice the upside down U, that stands for intersection. So subtract out the part that is both. And that's really the key to doing the addition rule. You have to decide, is this a case where there's a both, something they have in common between events A and B, or it's not. If it's not, then it's just the probability of A plus the probability of B, which is why it's called the addition rule. So, slightly different way of looking at it. These are with Venn diagrams. If A and B are totally independent, mutually exclusive, you can be one or you can be the other, then the addition rule just becomes PA plus PB. If, however, they do have some overlap, in which case we say they are not mutually exclusive, there is a both part, then when you add A and B together, you're going to get that little piece twice, and that's why you have to subtract it out. Now, basically, when we say that they have nothing in common and that they are mutually exclusive, we call that disjoint. Okay, in other words, the intersection part is 0. Another way of looking at it is PA and P not A. Remember when we put a little bar on top, it means not. PA and P not A cannot be true at the same time. Or another way of looking at it is if you take A and the not A, so in other words, you've taken all the possibilities that can exist, your answer is just going to be a 1. So again, disjoint, mutually exclusive basically mean the same thing. It means there is no intersection. There is no both case. Now, if you have 3 situations, so in other words, the probability of A or B or C, then the way that one works is it's the probability of A plus the probability of B plus the probability of C. And then notice that we have 3 subtractions here because when you have 3 circles that all interact, you have little overlaps 3 times, so we have to subtract each one out. And then it turns out that you have to add back in the case in which A and B and C are all true at the same time. It would be the intersection of all 3 circles at the same point. You have to add that back on because by subtracting each one of these, you subtract it once too many times. So, first what we're going to do is look at some examples of whether or not things are disjoint. Okay, you randomly select a Republican or a Democrat. Again, can you be the same thing? Can you be both at the same time? No, you can't be both. You're either one or the other. You could be neither, but you can't be both at the same time. Okay, randomly select a queen from a deck of cards or a spade from a deck of cards. This is not disjoint. There is a queen of spades. There is something that is both a spade and a queen. And so these would not be considered disjoint. And so what that means for our addition rule is after doing the probability of having all the queens and all the spades, those 2 separate probabilities, we would have to subtract out the queen of spades case because that had been double counted. Randomly select someone who is wealthy and someone who is homeless. This is also not disjoint. It's very unlikely, but it is possible. For example, there have been cases in which a homeless person has died and then they find out that they actually have quite a bit of money in the bank account. Or a slightly more believable situation, you live in the Midwest, a hurricane has just destroyed your home, you are temporarily homeless, but that does not mean that you couldn't also be wealthy. So sometimes it's not obvious that it can be both. And then here, a positive polygraph test result and the subject told the truth. Now remember, a positive test is the polygraph test is saying they lied. So can the positive polygraph test, can they say the test say they lied but they're actually telling the truth? And if we go back to what we had up here, that would be the false positive case. In this case, out of the 57 people that it said lied, 15 of them did not actually lie, and those are called false positives. False negatives are when they say they didn't lie, but they actually did. Almost all tests will have some false positives and false negatives. That's something that we have to worry about with the virus testing as well. Just because it says positive does not actually mean that you have the virus. No test is 100%. All right. So to move on then, now let's look at some probabilities using the addition rule. So probability a roll of dice that is less than 7 or odd. Now, please note, this is a paradise, okay, not just one. Otherwise, there would only be 6 options, and they would all be less than 7. But so we're looking at a paradise whose sum is either odd or less than 7. Well, less than 7, and think back to when we were doing the sample space, there are 36 possible outcomes with a paradise. Well, 15 of them have sums that are less than 7. 18 of the 36 have sums that are odd, and that should make sense, even or odd. Half of them would be odd, half of them would be even. There are 6 cases in which the sum is less than 7, and it's odd. So, for example, 3, 1 and 2, and 2 and 1, that's 2 cases where you could be odd. And then you have the ones that are for 5, that would be 2 and 3, and 3 and 2, 1 and 4, 4 and 1. There's another 4 more, so that would be 6 total cases. So, you got a probability less than 7, you have the probability that's odd, and you have the probability that's both. So, add the first 2, subtract the both, and we get 27 out of 36, or a 75% chance that when you roll a pair of dice, your sum will be less than 7 or odd. Okay, how about the probability a roll of dice that is less than 6 or more than 8? This one does not have a both case. You can't be less than 6 and more than 8 at the same time. Now, the probability of less than 6, there's 10 possible outcomes that are less than 6. So you can add up to 2, you can add up to 3, 4, and 5. Those would all be less than 6. Probability more than 8, there are also 10 out of the 36 possibilities for a pair of dice. So you could roll 4 and 5, 9, 5 and 5 at 10, and so forth. So there are 10 possible cases that are more than 8. So the probability here, notice all we've got is the add part. There's no subtract because there's no both. You can't be less than 6 and more than 8 at the same time. This one comes out 20 out of 36, or 0.555. In general, I always like the decimals better than the fractions, just because I don't want anyone worrying about reducing it to its lowest common denominator kind of thing. All right. Now, by the way, another way you could have looked at this problem was if we looked at the not case, not less than 6, or not greater than 8. In other words, what if it was just 6, 7, or 8? That's fewer cases to consider. Turns out there are 16 of them out of the 36 possibilities, which is 4/9. The case we wanted, which was what is the probability of getting less than 6 or more than 8, would then be 1 subtract the not case, which would mean 1 subtract the 4/9, which would get us right back to the 5/9 that we had before. The reason I bring this out is sometimes it's faster to do the not case and then subtract from 1 than it is to actually go figure out the other possibility. Alright, here we have a roll of 2 die whose sum is even or whose sum is a multiple of 4. Okay? Now, multiple of 4. There's 9 cases. It could add up to 4, add up to 8, add up to 12. There are 9 possible cases. 36 of them are even. There are 9 cases that are both, because of course every one of the multiples of 4 is also even, so that's all 9 cases. This one, even or multiple of 4, probability even, probability of multiple of 4, subtract the both case, we end up with just 50%. Just a 50% chance there. Alright, if the probability of rolling a 7 with a pair of dice is 0.167, what is the probability of not rolling a 7? And again, this is with a pair of dice, so that could be like a 1 and a 6, a 3 and a 4, a 5 and a 2, some combination of that. The chances are basically 1 out of 6. What is the probability of not rolling a 7? Well, the not can also be seen as 1 minus the given case. So since they already gave us this case, we can simply subtract from 1, and then we have the not case. So these always have to go together. The not and the original case added together has to get us back to 1. So if they give us either one, we can automatically find the other one. All right, what's the probability of not getting a 10 or a face card? So not getting a 10, a jack, a king, or a queen. Well, there's no overlap because 10's not one of the face cards. So this is just going to be the probability of getting a 10 or a face card. There are 4 10s, there are 4 jacks, 4 queens, 4 kings, so that's 16 out of the 52. We want the not case, so 1 subtract the 16 out of 52 gives us 36 out of 52, or just over 69%. Now, of course, we could have said, all right, not a 10 or a face card, so let's see, that's the 2s, the 3s, the 4s, the 5s, 6s, 7s, 8s, and 9s, and done it that way. Also, the aces are not a 10 or a face card, but there's fewer, just 4 times 4 basically, out of the 52 cards in a deck, and so we could get to our answer more quickly. All right, this is an example of an A, B, or C type problem. Okay, find the probability of A or B or C if, and then they give them to you. Here's the probability of A, probability of B, C, A and B both being true at the same time together, A and C being true at the same time together, B and C being true at the same time together, and all three, A, B, and C, all being true together. There's our formula. P, A, or B, or C is PA plus PB plus PC. Subtract PA and B, subtract PA and C, subtract PB and C, plus PA, B, and C. Plug the numbers in, and we get a just over 58%, 0.583 probability of this happening. And that does it for section 3.